All right, in this podcast, I'm going to review IMFs, intermolecular forces. I'm going to try. First of all, it's important to recognize when we're talking about intermolecular forces, we are talking about the attraction between one molecule and another. We are not talking about covalent bonds. Covalent bonds are very, very strong. IMFs are much weaker, than covalent bonds. You have to be very careful about the term bond. If you're writing an FRQ and you say bonds, the reader is automatically going to think you're talking about covalent bonds. So you don't want to say you have to break bonds. You want to, if you're talking about breaking IMFs, you have to say breaking IMFs. We're breaking a dipole-dipole. We're breaking a hydrogen bond, We're breaking IMFs, So bonds imply covalent bond, and those are intramolecular, within the molecule. Those are the covalent bonds. That's the covalent bond, intramolecular. When we say IMF, we're talking about intermolecular forces, the attraction between two molecules. Even though we said that the covalent bond is very strong and that the IMFs are weaker, they are still strong enough, though, that they can have significant impact on the physical properties of a substance, In particular, boiling points and melting points, vapor pressures, and even viscosities. And in fact, the best indicator of the strength of an IMF, how much intermolecular forces there are within a compound, is its boiling point. That's an indicator of exactly how strong. The higher the boiling point, the stronger the IMF. IMFs are sometimes called van der Waals forces. Van der Waals is a catch-all for all of the intermolecular forces. So we can have dipole-dipole interactions, hydrogen bonds, or London dispersion forces, and we'll talk about each of those. Now there's another type of attraction that's not really an IMF because it's not involving two molecules, and that's an ion dipole, which is really important in solutions. It's a very strong attraction between either the positive or the negative ion from a salt and waters. One of the things that's important when you draw these is that you do not draw this as negative and positive, because they are not ions. They are not negative and positive. It's a partial positive and a partial negative. So a dipole-dipole interaction means that I have a molecule where one side is more electronegative than the other. So this could be something as simple as I have HC, whoops, it would be the other way around. So it would be H, which is the more positive side, and Cl. And if I have this situation, I have more electron density on this side, and that is going to cause this side to be attracted, right? And molecules are going to line up. All right, so let's talk about London dispersion forces. London dispersion forces, all substances have London dispersion forces, even atoms. It could be a single atom. Here we have a helium atom. It's got 2 protons and 2 neutrons in the center, and it's got 2 electrons. And if I have these 2 electrons, which are constantly moving, it is possible that for even a split second, it actually shows it here, where these electrons are on one side of the atom, making one side of that atom a little bit more negative and the other side a little bit more positive. These are relatively weak. They're temporary. But what they can do is they can induce a dipole in the neighbor. So if I have one side that's more negative because it's got more electrons on one side, and I have another of the same atom, it is going to induce a dipole. The fact that this side is more negative is going to attract, it's going to cause the electrons to shift away, and I induce a whole series. It's like a domino, and I end up forming these attractions. These are IMFs. Okay. So the factors that affect London dispersion forces is, the most important is that the more electrons you have, the more polarizable you are. Okay, because if you have more electrons, there are more that can be shifted to one side. So the more electrons, the greater the London dispersion forces. And the term we like to use on the FRQs is, if they're larger, they have more electrons, and it makes them more polarizable. Now, if I have large molecules, let's say I have neopentane, which is a 5-carbon chain with hydrogens on it, or I could have, this is normal pentane, or I could have neopentane, where it's got a structure more like this. Still the same formula, but a different placement. The more linear molecule, the normal pentane, is going to have a higher boiling point. And that's because it has more surface area. Okay? So that's a subtle difference. It's not a huge difference here. But you might get asked about why one molecule has a higher boiling point than another, and that would be why. So if you were to look at some of these tables and you look at what they're showing here is as I increase molecular weight, I'm increasing boiling point, which might make you be inclined to say something like, what's causing a higher boiling point for iodine versus fluorine is that it has a higher molecular weight. But you don't want to say that. What you want to say is the cause of the higher London dispersion forces is the fact that there are more electrons. Never say it's because it's got a higher molecular weight or a higher molar mass or a higher mass. The higher mass is an indication that there are more electrons. It's all about the fact that of how many electrons you have and how polarizable you can then become, right? Okay. Okay, so there are times where, in general, we say that we have London dispersion forces, and then greater than that we have dipole-dipole forces, and then we'll talk about hydrogen bonds. But it's not really as simple as that. It's possible that you have substances that are non-polar only have London dispersion forces that have higher boiling point. So which is stronger? Well, if I have two molecules that are about equal size, okay, relatively small, same number of electrons, the molecule that's a dipole-dipole is going to win out. It's going to be a higher or stronger LDF, London dispersion force. But I could also have a very large molecule that's got a whole bunch of electrons, right? And a small molecule that's totally non-polar, right? And then I could have a small molecule that is has a dipole, and I can have this have a higher boiling point, okay? And you're not expected to necessarily know when the size and the number of electrons makes London dispersion forces greater. More likely you're going to be told molecule A has a boiling point of 200, and molecule B, which you'll be given some information about, has a boiling point of 150. And if you're given that boiling point, then you know this has stronger intermolecular forces. And if this is nonpolar, then it must be because it's got London dispersion forces and lots of electrons, even though this might be polar. All right. So this is a popular chart in chemistry textbooks. And what you're seeing is the impact molecular weight has on the boiling temperature. And in general, what you see here is as the size of the atom or the molecular weight increases, the boiling point increases. Okay? And the reason the boiling point increases is because you're increasing the number of electrons and you're becoming more polarizable. We could always practice saying those things. Okay. And we got the same thing here with this group. The big difference is that down here, carbon is pretty much within the trend, but I get this huge jump up here when I look at water. And the reason for that is water has a special kind of dipole known as a hydrogen bond, where I have a tremendously strong dipole. And I have hydrogen bonding whenever I have hydrogen bonded directly to a very electronegative element. And those electronegative elements are F, O, and N. So like E.T. says, this is phone home. So not only do let's say I have HF. You know, if I think about what H is like, it's got a proton and one electron and one neutron. So if fluorine is hogging the electron, you know, really what I have here is basically almost an exposed nucleus. So it's very much more electropositive, electronegative, because of this very large difference in electron density. So if I have HF, I'm going to have the F side much richer in electrons. Very strong dipole known as hydrogen bonding, and it's usually shown as a dashed line. Okay, so water can hydrogen bond with itself, or it can hydrogen bond with some other substance, or some other substance like ammonia can hydrogen bond with itself. So let's take a look at some of the properties affected by IMFs. Okay. So I can have, when we're talking about intermolecular, we're talking about, you know, if I have a liquid here, I've got some attractions between molecules within the liquid. That's what we're talking about. So vapor pressure is one. Vapor pressure is also an excellent indication of how strong your IMFs are. So if I have things in a liquid phase, particles are pretty close to each other. If they have dipole-dipole attractions, or even if they have strong LDFs, there's always going to be some number of particles at the surface that have enough energy that they can go away, they can shoot off as a gas molecule. So vapor pressure is always measured in a closed system. So if I have a bottle of water, I'll show you what a great artist I am. Yeah, crooked bottle. A bottle of water. I got all these waters down here. There will be some waters at the surface that break away as a gas. So vapor pressure is that pressure associated with that vapor. Okay? And as you can imagine, if I increase the temperature, I get more particles that get enough energy and they can escape. So at any given temperature, the number of particles, or the pressure created by that vapor, is going to be an indication of how hard it was for this particle to escape. How much energy did it take to get this particle to separate, to break the IMFs and go off as a gas. Okay, so the stronger IMFs are going to have low vapor pressure, because it's going to be very difficult for them to break away. So there's not going to be many particles up here. Okay, miscibility is a term that really means solubility, but when we're talking about it, we're talking specifically about liquid. Usually when we're talking about solubility, we're talking about dissolving a solid in a liquid, but this is whether or not liquid and liquid will mix. So water and gasoline don't mix because here's water, it's very polar, and gasoline is totally non-polar. So there's nothing that this non-polar substance can do to break the attraction between one water and another water, to break that hydrogen bond. Whereas water is miscible with HCl because HCl is also polar, and these like dissolve like is going to happen. Okay. Last thing we want to talk about here is we will talk about the difference between ideal and real gases, and the two differences is an ideal gas assumes no attraction between gas molecules, that they're too far apart, and so real gases do have some attractions, and the gases that act most realistically are those that have the strongest IMFs. All right, we're going to stop right there.